welcome everyone to Julie Bergner's great talk on the Waldhausen S-construction.
We'll see if you really want to call it a great talk before it started, but it's exactly the right length of title and the exact right number of co-authors to fit on this chalkboard, so let's get started. All right, so thanks to the organizers for inviting me to this talk, and thank you all of you for being here. So I'd like to talk about this project, the Waldhausen S-construction as an equivalence of homotopy theories. So I think I will just start by really briefly recalling the S-construction in the context of exact categories. So I just want to assume I have an exact category. So I have some category, and the key information here is I'm going to have some admissible monomorphisms, admissible epimorphisms. Okay. And then I'm going to define Sn of C to be the groupoid of diagrams of the following one. Okay, so we have things like this. So we have all the horizontal arrows are in M, our vertical morphisms are in E, and we want all the squares to be bicartesian, so both pullback and push-out squares. So if we do this for all n, and then we get some simplicial object in groupoid. So the simplicial structure is just given by, say you wanted to apply the second face map, then you just remove everything that has a 2 as an index. And then just sort of compose some arrows and you get something down, and then you can insert rows just via identities. So we take the collection of all of these, we get a simplicial groupoid. And so in particular, its nerve is, well, depending on whether you want to work in simplicial sets or spaces, I'm just going to say the nerve is a simplicial space, by which I really mean and I'm just not going to distinguish in notation from now on. I'm basically just going to work with the nerve. Okay, so then a question that you might ask, although I don't know to what degree, it's not a recent construction, but I don't know that this question was asked until more recently, and that's that what kind of structure does this simplicial space have? How could you identify something that maybe came from this construction? And the answer was given, one answer to this was given roughly at the same time by two sets of co-authors. So first by Dyckerhoff-Kapranov. So many of you were here to hear Toby Dyckerhoff talk about this 2 weeks ago. And this was also done by Galvez-Carrillo-Kock-Tonks. And they said, well, this is, so using the language of Dyckerhoff and Kapranov, this has the structure of a unital two-Siegel space. And although it's the same notion, this set of authors would call it a decomposition space. So the next thing I need to do is tell you, this might be less familiar, again, especially those of you who weren't here for Toby's lecture series. So what is a two-Siegel space, or unital two-Siegel space? Well, let me first tell you what a Siegel space is. First of all, because the definition of two Siegel space is going to build on it, but I'm also going to need Siegel spaces later on in the talk. So this is and again, it's a flavor of some simplicial space. So a Siegel space is a simplicial space X such that for every n at least 2, the Siegel maps here, where there's n copies of x1, that these are weak equivalences. And there's one of a couple ways to make this homotopically meaningful. I can either make this a homotopy limit over here, you can put h's here, or I can assume that x is refibrant or something, in which case I can leave it alone. I'm going to not add that notation here, but know that everything is really secretly a homotopy pool. Okay, so we want to generalize this definition to a two-Siegel space, but what's helpful is to just remember where these maps come from. There's different ways to describe this, but one way to do it is to take a string of n arrows, label those, and just think of them as sitting inside of the n simplex. This is sometimes called the spine. So for example, when n equals 2, you just have this, just 2 arrows fitting into the 2 simplex. And then, given any simplicial space, if we just think of, these are simplicial sets naturally, but I can think of them as discrete simplicial spaces. So there's two ways to think. You can think of it as a constant simplicial object. I don't want to do that. I want to do the discrete. So we can then map them as discrete simplicial spaces into our simplicial space X. So we tend to use Charles Resk's notation for this, which is Gn. So we can take maps from delta n into x, and we get a nice map here to maps from Gn into x. And this is just xn, and then this guy is just the right. So that's one way to think about where that comes from. So, and just a reminder, so what this does is that one of the things these maps do for us is this structure, if we have a Siegel space, so it gives X the structure of a category up to homotopy. And we can see that by just looking at the first of the Siegel maps, when n equals 2. So you have the two, so D2 and D0, the face maps, but then you have the middle face map. But then because this map is this map here, the Siegel map, is a weak equivalence, we can think of, well, up to homotopy, we have an inverse, and therefore we have an up to homotopy composition. So that's what we're thinking in the back of our mind when we have Siegel spaces. We've got some sort of structure like a category. All right, so what about, so that's Siegel, or sometimes called one Siegel to emphasize. What we really want is two Siegel. Well, we can think of this as having a one-dimensional flavor to it, because this string of arrows, we can think of that as just being a triangulation, if you will, of just a line segment. You've just chopped it up into little pieces and then somehow assembled it onto the n simplex in some way. And now we'd like to take triangulations of something two-dimensional, namely polygons. Okay, so the simplest case, simplest non-trivial case, is where we just have a square. I'm going to label these. So I've got two different triangulations, either by adding an edge from 1 to 3 or an edge from 0 to 2. But in either case, I can think of including this into a 3 simplex. And you can see that in this particular case, we get the two halves of the boundary of the 3 simplex. Seeing what the labels are here. So if I give these names, say T1 and T2, I can do the same thing here and just say, all right, these are, well, these sort of as defined are simplicial sets, but I can think of them as discrete simplicial spaces, and then I can map them into an arbitrary simplicial space. So I can map x3 into x, and then I can either map in T1 or T2. Again, here we'll just get x3. And here, well, these both look like two copies of x2 glued together along x1, but the gluing is different. It's not the same pullback in each case, because it's going to depend on the triangulation. And then if you have polygons with more sides, you're going to have a lot more possibilities for triangulations, and hence a lot more maps of this kind. But we can just say, okay, well, take all the maps of this kind and ask that they all be weak equivalences. And that's going to be our definition of two Siegel space. So we have a simplicial space X such that for every n, at least 3, and every triangulation T of an n plus 1 bond, the induced map from Xn, and now we will have n minus 1 copies of x2 glued along x1, and we want that to be a weak equivalence. But then then you can ask, so if a Siegel space looks like something that behaves like a category, then how should I think of the structure of the two Siegel space? Well, let's look at this same kind. Now we don't look at the same kind of diagram as we had up here. We don't know anything about this map anymore. But you could say, okay, take a pair here and just look at its pre-image, which it could be multiple things in the pre-image of a point here, there could be nothing, but whatever it is, you could send it over. And so you could say, okay, this is something with a partially defined or multiply defined composition. And this is something, for example, Siegel looks at things like partial topological monomics and things like this. So it's that kind of a thing. But what's nice, if you stare at this picture, you can see that this composition is still associative. So you can think of this as, you know, these two different triangulations sort of encoding. If you had arrows 0 to 1 to 2 to 3, you have different ways of composing, but they determine the same 3 simplex autonomy. So when it makes sense to ask if something's associative. So are there any questions?
Are you going to do the S-dot construction as an
Right. So now we can sort of come back and say, well, here we go. They show that we actually have that. This is a prime example, and this is interesting in that, I mean, I've followed the way that Dyckerhoff and Kapranov treat these. Their approach, this set of authors, is quite different. They're really more starting at this point and saying, well, I want to look at something that has this kind of structure, and how do I understand it? They don't define it in terms of two Siegel maps. And they both come up with very different examples, except they both come up with, hey, we can feed in an exact category into the S-dot construction, and we get something two Siegel. So it's very interesting that they both identify this. Or you were asking if you want more details about?
Oh, yeah.
Oh, you want more details? Oh, okay. All right. Well, let me see if I can do this on the spot here. So if you look at, I knew I should have written this down. I should have known somebody was going to ask. So if you look at, let's say this T1 here. So the maps here, so we'd be looking at, so I'm including this into delta 3. So my two maps here would be given by D0 and D2.
So X3 then means so you're looking at one of these three.
Right. So what does this? So what does this mean if X is S dot of something? Well, X3 you would want. So you have this. Okay, so, but then what do we have over here for looking at this map? So if we have D0, if we took D0, that would be, let me use some color here. So D0 would just be where we truncate. So that would be that part, and then D2 is the more interesting one. Oops, sorry, so I want D2, that means I'm gonna leave off everything here. So that means I have this. I still have this. I have this map. Oh, I don't have that one. I have that one. Okay. So, all right, so having something in X3, I can just get the pink and the purple diagrams. The more interesting part is, okay, how could I recover if I had just the pink and the purple? But one of the things we can do is say, well, we can take, we've got this span here, we can take the pullback. So this is what we'll call A02. And then the universal property is going to tell you the two. And then, well, okay.
Am I allowed one more?
Yes, go ahead.
So, I mean, this idea of partial slash multiple composition, can you also, so now X1 is like a, you can sometimes compose these, you can think of like, you know, one simplices in the S-dot construction as morphisms that you can sometimes compose, and sometimes not, and sometimes in several ways, maybe I have.
Right, so I
depending
guess.
whether there exists a lift, and there could exist potentially several.
Right, so that, I mean, what that's saying, if you're doing a composition, then what you have, let me not put labels on anything, I mean, still denote the zero object, but you're saying you have something like this. And so the question is, well, can you complete this to a square? But that's not a pullback or a push-out configuration, so maybe you can fill that into a square, maybe you can't.
And maybe in several ways.
It may be in several ways, yeah, for sure. Yeah, but there's nothing, you can't say anything special.
The different extensions that you would get between those.
Yeah, exactly. Okay, and I'll add.
But what does it mean associative?
Yes.
You make choices in the position along the way.
Well, it's associative up to homotopy. Like it may not be I mean.
Independent. I mean, if you have different choices.
Oh,
and then
right.
You do. I mean.
So I mean, given that you have, you know, once you have, but I think the short answer is yes. So I mean, there might be different ways to compose, but once you've selected a way to compose, I mean, then. Because if you're asking about associativity, you sort of, okay, it's more complicated, but.
But
up to
associativity is up to higher homotopies.
Yeah. Whatever you've chosen.
Whatever you've chosen.
So, I mean, maybe there's multiple ways to do part of the composition and it should work whatever choice you make.
Okay.
All right, but there's one word I haven't explained in the, I guess it was what used to be on this board, which was S dot has a structure of a unital to Siegel space. And I don't want to spend a lot of time on this. Unital is just going to mean that identity maps behave. So you have identity maps just by your degeneracy map from 0 to 1, but you want identities to act like identities so that you can compose and it doesn't change anything. And so this unitality condition is just something we build in so that that's true. It's not that hard to describe, but just saying this is enlightening enough for our purposes. Okay. So I basically talked about this for exact categories, just because that's maybe the most familiar thing. But there have been a lot of generalizations of this that still work. So Dyckerhoff and Kapranov talk about proto-exact categories, where you sort of drop the additive structure on an exact category. And then you can do like stable or exact or proto-exact quasi-categories, so you have more homotopical input, and it still works. You still get a unital two-Siegel space. So the question that you would ask is, okay, how far can we keep generalizing this? And I will add, this does not work for general Waldhausen categories. So when you sort of only have a notion of cofibration or monomorphism, but you don't have, so where you're in a world where you only have push-outs, you don't have the pullbacks, then you don't get all of this. So this really requires, we sort of need to be able to go in those directions. So we can't generalize that far, but the question that we had was, is there a way to describe the most general input? To an S-dot construction. Let me refine, there might be different ways to answer that question, but somehow is there an input, so is there a kind of input such that S dot induces some kind of equivalence? And in fact, we're going to do this so that we get an equivalent equivalence of model categories. But to answer that, so
Where you want the target to be two-Siegel.
right, so we want to input something, hopefully as general as possible, that an S-dot construction makes sense, and then out, but still get something two-Siegel as an output. So to answer this, we're saying, well, what are the really important things? I mean, when we're building this construction, what are the key features that we use? So, for example, an exact category is an additive category or something. We didn't use that structure at all. We didn't actually use it. These were really like monomorphisms and epimorphisms in some formal sense, or some technical sense, but we just needed them to behave in certain ways. So that leads us to our general, so the generalized stuff. Okay, so the first thing that you might observe is, well, we've got two kinds of morphisms. So in the case of an exact category, this was coming from your monomorphisms, your epimorphisms, but we've labeled them accordingly. So we want and we're thinking of these as somehow the horizontal morphisms, the things that we put into our diagrams horizontally and the things that we put in vertically. And then you assemble them into some kind of squares. And this kind of structure is what's known as a double category. So a double category is basically where you have objects. You have two different kinds of morphisms that are called horizontal morphisms and vertical morphisms, and then you have squares that are part of the data. And if you like a lot of category theory language, this is a category internal to category. So it's the really formal way to say it. If you don't like that, then just think of something like this. So you just have a lot of pictures. I'm going to use the same kind of notation as before for horizontal and vertical, but saying these diagrams commute or are Cartesian or co-Cartesian or something doesn't make sense anymore because these two kinds of morphisms don't necessarily live in the same world. There's not necessarily a common category in which they live, in which you can compose things, but you can still say, okay, I have some kind of data of allowed squares. But like with Siegel spaces and two Siegel spaces, I don't want something as strict as an actual double category. I want something like a double category up to homotopy. So what I'm going to do throughout here with each of these steps is just write down what the kind of categorical flavor we want to have, and then write, okay, what's this look like homotopically? So homotopically, this should be what's called a double Siegel space. By the way, is the purple chalk okay? Is the green chalk better? Okay, so a double Siegel. Sorry?
Fantastic, actually.
It's fantastic. Okay, wonderful. It's fantastic. So what's a double Siegel space? Well, we just do the Siegel condition twice in two directions. So this would be a bisimplicial space. This is why I like calling them simplicial spaces here, so that we don't go too crazy. So this is a functor from delta op cross, so I call it x, from delta op cross delta op into simplicial sets. So such that if I fix one direction, so that's a star and a k, and if I fix in the other variable, so x, k star, that these are Siegel spaces for every. So I just have this two-dimensional grid, and I just say, okay, take any row, take any column, that's a simplicial space, and it should be a Siegel space. So that's our homotopical version of this double category. Okay, so that's going to be the first thing we want. But the second thing was we had some assumptions about squares. So back in our original construction, the squares were not just arbitrary, any old squares we wanted. They needed to be bi-Cartesian squares. Well, as I just said a few minutes ago, bi-Cartesian isn't going to make any sense in the context of a double category, because for that even to make sense, the horizontal and vertical things have to live in the same place, and they don't necessarily. But we can have the same kind of fillability condition that we had before. But what we want is that if we have a square, we want it to be determined by either its span or its cospan. So it's either determined by this information, so it's the analog of taking a push out, or it's determined by the thing that has the flavor of a pullback. And again, you can say, well, is this actually determined? So if we were in a double category situation, then we'd want to say, okay, this is uniquely determined. Once I have the span or the cospan, I get a unique square that fills it in. You want the homotopy version, then you just say, well, determined up to homotopy.
What is the meaning of the or? There are two types of these squares? Those
No, it means that if you have this data, it determines the rest of the square. It also means that if you just have this data, it determines the square. So if you have either kind of this information, you know that there's either kind of thing, it can be uniquely relevant.
So these squares live in x11 or?
Yes. Yeah, so there's some kind of pullback sort of condition that you can impose. So if you have, so say, okay, one of these lives in x10 and one lives in x01, and you want to be able, and if they fit, something in one place here and they share a target, then you want to find something in x11 that fills it.
I still don't understand. So, what's the condition? Determined up to homotopy.
Right. So what you should have. So say look at this one. So something here would say you'd have something in x01 and you'd have something in x10. So these are your. So one of these in code is like your space of horizontal versus vertical. Yeah, not there. And then they have to agree. Then they would agree along. I guess it would be. I guess what way I've written it, it'd be an x0. Maybe I don't want to specify both of these.
You're saying that should be weakly equivalent to the other thing.
Yeah. Well, I may be getting too specific with the other. So this should look something like x. No, that's right. Yeah.
And are there higher conditions or just on 0 and 1 stuff?
You have to worry about things working higher up as well. Yeah, it gets kind of.
But if we're interested, we should see the paper.
If you're interested, you should see the paper, which in the homotopy case is not quite done yet, but it will be. So the discrete case where we do everything just in double categories, you can look at that one for now. This one will be done soon. All right. Or you can ask me and I'll show you the page from the direct. It gets pretty messy pretty fast.
But what's the idea of the higher homotopy?
I'm sorry?
What's the idea of the higher homotopies? What?
Well, I think if you have, you just want everything to then fit together. So once if you have a configuration like, I guess at this point you don't need it. I guess at this point we don't really know that. I think you don't really need anything else here because you're just talking about the squares. At some point you have to worry about, if you have a bigger diagram and you have, like when I talked about the things being, being too seagull, where you have like a bigger diagram and then you're like filling in a square, then you sort of have to make sure you get composites with the other squares, for example. So, you fill in a square, it's just like, if you have a category, you throw in an extra morphism, it's not enough to just throw in the morphism, you then have to compose it with everything that makes sense to compose with, and it's the same thing here. You have composition of, I didn't talk about the ins and outs of double categories and how they work, but, you have to have compositions of squares and things like that. So sometimes, when in a larger context, you have to worry about, okay, you put in a square, but then you have to make sure it plays well with any squares that happen to be around. But I don't think that's actually what we're worrying about.
So you're just sort of making sure that it has,
Yeah.
you cannot talk about Cartesian squares, but you're just putting in the inversion property.
Exactly.
So,
All right, now we've got one more thing to worry about, and that is, so as we've described it, S dot requires the zero object. So these are these little stars that appear along the diagonal. So, well, maybe your zero object isn't unique, but it's unique up to some contractible space of choices or something if you're in some homotopical setting. But this would only give us, so notice in particular this would mean that S0 is always contractible. And that would only give us, so that means that we only get reduced up to homotopy two Siegel spaces. But we don't want that. We actually want to get something more general if we're really trying to get all unital two Siegel spaces. So what we want, so let's add this here. So what we want is something we call an augmentation. So we want to be able to put more interesting kinds of things along the diagonal in S dot. So to get more interesting, we instead use what we call an augmentation. So we want to have choices for things to put along the diagonal, but they're going to still have some kinds of universal properties. So this is going to be a subset of the objects. I'll call it A for augmentation. So such that for any object X, there exist unique, so you have a unique A that's initial with respect to X, and unique B, which is terminal with respect to X, with A and B in the augmentation. And so this is when you have those diagrams for the S dot construction, you always just, okay, we just stick the zero thing because it has the universal property. And we're saying, well, you don't have to have the same thing satisfying the universal property for every single object and in both directions. You just have to have one thing in each direction for each object. And this is what we call an augmentation. And then you can do the same thing. So the homotopy version, again, is again, you just have, unique up to homotopy. But in fact, you have to do a little bit more, because here you're saying, well, I have a diagram. I've been using a bi-simplicial diagram of simplicial sets, but I somehow need an extra object to pick out this augmentation set. And so we index by a category that we call sigma. And what this looks like is just you stick an extra object onto, being sloppy here with delta cross delta. I'm not putting all the appropriate brackets. So here's your delta cross delta, and we just stick in this extra object that we call -1, brackets around it, and now you take functors from sigma op to simplicial sets. And now you somehow get this extra space getting picked out that take opposite, and then you'll have an arrow here, and so you'll have a map from this augmentation set sitting inside your objects.
This would take care of the mapping into, but you also want the mapping out. Is this was coming from this structure of sigma the same way?
No, well, so all this diagram, there's two steps here. There's first of all the diagram, and all the diagram does, we would then get, so you would just get a map from x -1 to x 0, 0. So these are like your objects. This is your space of objects, and this would be your augmentation. So you think of the image of this map as like your subspace of objects that are in the augmentation. But then you have to impose conditions so that this universality holds. Just having the diagram doesn't tell you either one, actually. So you're looking at then, the maps, from here to here and here to here, that are gonna give you these kinds of diagrams, and that you can't have too many choices.
You have a nice example, maybe not the homotopy version, where you have such a structure where you have more than one, initial and terminal things, but they depend on your x.
Take a disjoint union of exact
I don't,
categories.
you don't
Okay, sure. That's the
Take a
cheat
disjoint
example.
union of exact categories. Take a disjoint union of exact categories, then whatever category you're in, different zero object.
Then you have two different kinds of zero objects.
Okay.
We do have some more interesting examples in the discrete version paper that we have, but that would be a long digression, so I can go into it here. Happy to talk about it later. Okay, so now that I just erased it, for number 2, did I give that a name? Did I give that a name? Sure did. So 2, the condition is called stability. And again, it's just sort of reflective of this idea, stable world where you have push-out squares, rollback squares are agreeing.
1 and 3 get names?
Well, 1 is double Siegel, 2 is stability, and 3 is augmented. All right, so you put this all together. The structure that we claim that we want are augmented, stable, double Siegel spaces. So you claim this is the really nice general input to the S-dot construction. Okay, so what we'd like to do then is to have model categories and a comparison. So the first thing we need was already done by Dyckerhoff-Kapranov, and that's that there is a model structure on the category of simplicial spaces with fibrant objects. The unital 2 Siegel spaces. For people who are experts on this, you just take the injective model structure and just localize with respect to some things that give you these unitality and 2 Siegel conditions. Okay, but these things were new, so we needed a model structure there. So there is a model structure on the category of these functors from sigma op into simplicial sets with fibrous objects. The augmented stable double. And furthermore, it's equivalent to this. Well, I'll just say that there is, think of S dot, so this should go from this category here, and I mean, there's a nice precise way to say that what this functor is, but it's going to do what you think the S dot should do because it's exactly how we've designed these things. So, and this inducer, and it's the right adjoint of equivalence. So that's what we were hoping to do. And I will add, because our motivation here was to talk about the output of the S dot construction for things like exact categories, which are spaces, that's how I've given this whole talk, but you can actually replace simplicial sets throughout with any Cartesian model category. So there wasn't really anything special about taking augmented stable double Siegel spaces. You could take augmented stable double Siegel objects in some sufficiently nice Cartesian combinatorial model category or something. So in the last few minutes, I just want to say a little bit about how this recovers the original construction. So, I mean, we have this whole generalization, but if we took this functor and it doesn't recover previously known S dot constructions, then it's not much of a generalization. So I want to say something about that. So to do that, I want to say start with an exact category, and then I want to produce from it an augmented stable double Siegel space. Here's our definition. So take an exact category. And then its exact nerve is denoted by n upper E of C. So we want this to be a functor from sigma op to simplicial sets. So given by the following thing. Well, I've got sigma op, so I have to tell you what it is in every sort of bisimplicial object. the bisymbol location, but then I also have this extra object. So I'll start with the extra object. So NEC in -1, this should be our augmentation space, then this is just going to be the nerve. And you don't have any fancy augmentation here, it should just be the 0 objects. So we take the nerve of the groupoid of 0 objects. Okay, now what about in any PQ? So basically, then I just want to take grids of the appropriate size. So this is the nerve of the groupoid of grids. So where I have my P's and Q's turned into different letters. Again, just with all squares by Cartesian. And then so we have two things here. So first of all, this is in fact, this exact nerve is in fact an augmented stable double Siegel space. And secondly, that if we take the diagram, so if we start with exact categories, we can either apply the traditional S dot construction to get a unital 2 Siegel space, or we can apply this exact nerve to get not so horrible notation here, something like double Siegel augmented stable, something like this. Or we can apply this new and improved S dot, and this should continue it up to Homotopy. And then lastly, we can prove this same kind of result if you go into quasi-categorical versions. So exact quasi-categories, stable quasi-categories, proto-exact, I mean, how these general constructions, we also, you can define a similarly flavored nerve, and you're still going to have this same result. So I'll stop there.
Questions?
She asked all the
Okay.
So I'm not an expert on this story, but I guess there's a story about S dot as a suspension in some context. Is there a relation between that story and this one?
I'm not familiar with that story. If anybody,
So I can't help you.
if anybody knows that story, I'd love to hear it. I haven't thought about it.
Well, if the exact structure is split, then it's a suspension. I don't know what else to say about this case, though.
Oh, okay. I mean, I know we have a very short little comment that I don't know, one of my co-authors wrote, and I'm still trying to figure out, what's going on with it. That if you start with something that's split, you could make sense of that story, and in that case, I guess it intuitively makes sense. Then what you get with an S dot construction is not just 2 Siegel, but it's actually 1 Siegel. So then you do have composition because you can have then putting arrows going the other direction in certain situations. And so then, if if you have something like, you know, here to here that's not a push out or a pullback, but then if you can have an arrow going back, well, then you could get something. I'm not the one that's thought about that in depth, so I'm not the best person to answer it, but in the case of this split business, there's a little bit.
Yeah, a question about the theorem. So, I mean, S-dot must have a left adjoint.
Mm-hmm.
So this is determined by what it does to delta cross delta. So do you know what the image of that
Yeah, so
left
we
adjoint
actually,
under? I mean, like if you take two.
right, so we actually have a good description. So in fact, the way we actually define this is the other way around, and this just happens to exist as a right-hand extension. So you have a functor from sigma to delta, which sends, it's going to send this -1 to 0, and then it's going to send some like p cross q will go to, I think it's p plus q plus 1. So it's some kind of like decollage type functor.
I see. But I was wondering about the adjoint of S-dot.
Right, so this is what induces the adjoint.
Oh, I'm sorry.
Yeah, so this induces the functor.
Oh, actually, yeah, right.
This induces the functor this way, and then S,
Yeah.
and then S dot just happens to exist as a right adjoint.
Right.
So this is actually the one we can get our hands on better. I just mentioned this one because I've been talking about S-dot construction for an hour. But this is actually, in terms of simplicial things, this is the easier one to describe.
I guess you're interested in this because you want just to understand the most general version. But are there what
Like, why else do you care?
what
Is that
examples
you're
what
asking?
examples are there sort of natural things which?
Well, so that's, I think that's really the next question, you know, so at this point, so we got started on this was a women in topology project, and I mean, the starting point was just very much, hey, there's these two single spaces, they seem interesting, what's something that we can do with them? And this is, you know, a nice question, I mean, especially motivated by, this seems to keep popping up as an example. But I think, yeah, I think the interesting thing is then, so if you had something that fit into this framework that didn't fit into something that we already know about, you know, I mean, S-dot construction is about K-theory, so do you have, you know, do you get some interesting kind of K-theory from something that doesn't fit into a framework that we already knew? So, so something I want to talk to Ina Zakarevich about, so she and Jonathan Campbell have some different flavors of K-theory that just the way they talk about it feels very similar to how we talk about this construction in two Siegel spaces and stuff. And so I'd really, I mean, maybe but I don't know that it fits into it. I don't know enough about it yet to know whether it fits into something already known, but I'd like to understand how we can understand it from this point of view. And just more generally, can we do something here? And that's, you know, that's something we haven't had a chance to explore just yet, but very much so. Anybody has an idea, I'd be happy to talk about it.
Anybody else? All right, we're going to unleash the cookies at this point. Yes, thank you. Join us back for the coffee break.
So I'd like special credit for cookies. Make sure you express your appreciation.
Or more importantly, tell me which ones you like and don't like.